So I'm going to be talking about the Radix tree, which is a data structure that, among other things, underpins a pretty common container in Haskell called data.intmap. But nothing about the data structure here is specific to Haskell. And so I'm going to walk you through how the data structure works with a little bit of detail about what it looks like in Haskell. And then I'll also talk about what we can do in the future to make this data structure better and to hopefully use this to build a more efficient, persistent key value map that we can use for functional programming. Now, the first time I actually got interested in Radix trees and in data.intmap was when I was doing some code with graphs. Now, graphs are traditionally one of the more awkward things to do in a functional style. What happens is that a lot of the algorithms that people have developed for graphs traditionally are written and designed in a very imperative style. And the traditional representations that people use, the adjacency matrices, for example, tend to be very awkward to translate into a persistent setting. So one thing I found is that there are a couple of Haskell libraries that take a different approach to doing graphs. And in particular, they create an interface to working with graphs that feels legitimately functional. And to me, this was a big deal, because for a lot of what I was doing, I didn't care about having the ultimate performance for my graph operations. What I cared about was having code that was reasonably fast, but also pleasant to write and easy to work with. And I remember thinking that what I really wanted was some way to pattern match on a graph and to write recursive code in a way that's very similar to how we work with normal trees and lists in functional programming. And as it happens, there is a library that lets us do this in a particular kind of way. It's called the Functional Graph Library, or FIGL, and the way it works is by giving us a fundamental operation where we can pick apart a graph by focusing on a node, doing an operation on that node, and then recursing on the graph with that node removed. So you can think of this as very similar to how we write list code, where we look at the head of the list, we do something, and we recurse on the rest of the list. But for graphs, it becomes significantly more complicated, because graphs themselves don't have a kind of linear structure like a list. And if you're interested in this, it's really worth reading more about the functional graph library specifically, but I'm going to focus on the data structure that they use to actually make this possible and relatively efficient. And once I looked into how the functional graph library was implemented, I found that it actually used a common container that a lot of other Haskell programs use. And in fact, a lot of code I've written uses it. And this is a container called data.intmap. And basically, it is a key value map where the keys have to be integers. And by forcing the keys to be integers, we can use a completely different data structure than data.map or data.hashmap, and we can offer a different set of operations. So today I'm going to walk through how this data structure works. I'm going to talk a little bit about what the data structure looks like when it's realized in Haskell, and I'm going to talk about how the same idea generalizes to more flexible and more efficient data structures in the future. So the idea behind these Radix trees actually goes back to, I think, the mid-70s with this paper called PATRICIA, and the data structure was called PATRICIA Tries. And apocryphally, I believe that the author of the paper had a daughter named Patricia and really went out of his way to make the acronym spell out her name, which is why it actually expands to practical algorithm to retrieve information coded in alphanumeric. Now, this is a lot like those NASA algorithms you hear, acronyms you hear for the various space programs, where clearly they came up with the word first and then tried to force something in. So these days, this structure is often known as a Radix tree or some kind of prefix tree as a kind of more common name for it. Okay, so apart from graphs and apart from just being a container, the IntMap data structure really has a few interesting properties that other common container data structures don't. And this was, I think, the original motivation for looking at a PATRICIA tree, a Radix tree, in a functional setting. And there was a paper by Okazaki and Gill a while ago. And that was that these maps, apart from giving us good behavior for common operations like lookups and modifications, also make it relatively easy to write a fast merge function where we can take two maps and combine them while doing some operation on the keys that exist in both of the maps. So that's one upside of using this structure. Now, another upside, and I think this one is very interesting, is that by the nature of how a Radix tree stores its data and how it stores its keys, we can do efficient prefix operations. So with a hash map, one of the fundamentals of using hash maps is that the structure of the keys and the order of the keys is completely lost. In fact, that's part of the reason that hash maps can perform well in the real world. But it also means that getting all of the keys out again in a sorted order is an expensive operation. So IntMap lets us not only get all the keys out in sorted order, but also efficiently do operations on all keys that share a certain prefix. Right? So we can relatively easily, in fact very easily, look up every single entry in a Radix tree where the key has a given prefix. And then we can also do operations on a big Radix tree, applying a function, for example, to every single entry that has a key with a prefix. Do you have a question?
Yeah, sorry, when the keys are integers, right? So by prefix, do you mean a number of digits?
Yeah, well, or in this case, the keys are treated as binary data. So it would be some pattern of bits. Yeah. Okay. And in particular, while Haskell's IntMap has integer keys, and this gives us some efficiencies, just in terms of constant time operations, there is no reason, fundamentally, why you couldn't implement the same data structure for arbitrary length keys, for example, using byte string. And in fact, there is a package on Hackage that is exactly the same as IntMap, except implemented for byte strings instead of ints. And in that case, you can have much bigger keys with presumably much bigger prefixes. And all of the underlying properties are the same. So one neat thing that is actually really handy with these prefix operations is that you can often take two different keys in your domain, especially if they have a nice hierarchical relationship, and combine them into a single integer. So then instead of having a nested map or some kind of map with tuple keys, you can have a normal int map which represents more structure. And in fact, right now at work, I'm looking into using this trick to make some of our simulation code a little bit more efficient, because there we often work with data that is first identified by the location it is at. So like, which target store are we talking about? And then identified by the specific item we're talking about. And if you can combine these two into a single data structure, there's really very little overhead to working with this kind of tiered data, first by location, then by item. And so IntMap, with its prefix operations, lets us do this in a way that would be much harder with something like a hash map. Okay, so now that we have more of a feel for what IntMap gives us, and especially what IntMap gives us compared to some of the other really common containers used in functional programming, let's take a look at how it actually works under the hood. So the most basic idea, the kind of data structure this really is something called a trie, or a tree. Now, most people pronounce this particular word as trie, because the word tree already exists. But originally, the word trie came as a part of the word retrieval. And so I believe the person who coined the term really wanted everybody to refer to these things as trees. But for whatever reason, that never really caught on. Okay, so what is a trie? Basically, it is a data structure, a tree, that stores a key, but reads the key in component by component. So unlike a binary search tree, where you deal with keys by comparing them according to some order, a trie actually deals with a key part by part. Now, in principle, what this part might be depends on the kind of key you're working with. And if you're working with string keys that might have letters A, B, C, etc., you could have a data structure that looks like this. And the idea is that if we needed to look up the key B, we would go to the first letter in the key, which is B. We would choose the branch that corresponds to the first letter, and we would have the value attached to B, which in this example is 1. And if we had a longer key, we would start by doing the same thing, going to the first letter. Then, once we've branched on the first letter, we repeat the process and branch on the second letter. And then finally, we branch on the last letter of the key and get the final result. That is that the value at the key BAB is 7. So that is the fundamental operation that tries are designed for. They're designed for reading in keys part by part and branching on each part. So you can immediately see that while it is under the hood a tree, it behaves very differently from binary search trees. Because instead of constantly comparing keys against other keys for order and relying on some measure of balance, we just read the key in. And in fact, our operations in this very simple model have performance that depends on the length of the key, but not on the number of elements in the data structure. So the asymptotics behave in a fundamentally different way than they do for a lot of other tree-based data structures that we're used to working with. Okay, but let's go back to what I was talking about with efficient prefix operations. Let's say, given the previous example structure, we wanted to look up every single key value pair where the key started with the prefix BA. How would we do this? Well, we start out exactly the same way we did as when we were looking up a single value. We start by going to B, and then we go to A. But the difference is, because we expect to get some container out, we're saying every single mapping with this prefix, we just return the part of the tree that we navigated to. So in fact, getting this part of the tree was faster than getting specifically the element at BAB, because we only took 2 steps and just immediately returned everything from that point onwards. And so as we'll see, even as we make the actual implementation of the tree a little bit more complicated, the fundamental operations and the behavior of those operations remains just like this. And so for the same reasons that we can look up a key in time proportional to the key length, and that the same reasons why we can look up prefix queries efficiently will remain true even as the actual structure gets more complicated but more efficient. Okay, so again, the idea here, at least for the basic try, is that we retrieve a key character by character. Okay, so what is IntMap? Well, IntMap throws in another complication, I guess, on top of this. And so the first thing is that IntMap is a binary trie. And in this case, when I say the word binary, I mean that IntMap works bit by bit. So instead of considering characters in some arbitrary character set, IntMap does it by taking a look at the actual bits that make up a key and reading those and branching on those. And if you think about it, one of the difficulties that I completely glossed over in the previous picture with a trie made up of letters is what must each of the nodes look like? Because here we might have an arbitrary set of letters for the keys. And in fact, if we were working in Unicode, right, there's literally thousands upon thousands of potential letters in our keys that we would have to branch on. And so that means that each container, each node here, would have to have a data structure of its own to work with, human letters. And by going to a binary system, we know exactly what possibilities we have in each node. In this case, we have 0 or we have 1. And so this means that the node itself can be a very efficient, kind of simple data structure. It doesn't have to have a lot more structure to deal with the complexity of real-world letters, because we're just operating bit by bit. Now, on the flip side, the problem with this simple model is that even for a short key, if we create the full tree and we instantiate every single path, every single possible set of bits, the trees get really big really fast, right? In this case, we're only looking at 3 bits at a time, and we have a tree with 8 elements. And if we were looking at 32 bits at a time, then we would have a tree with, what, 2 billion elements? So as you can see, we really need to do a little bit more to make this practical. So what we do is we take a look at the structure of more sparse trees. So what happens when we don't have too many key value pairs? And then we figure out how to compress these trees and to make the data structure a lot more efficient and to avoid wasting space on any branches that we don't need to take. So the first step here is a thing called path compression. Now, it's pretty common to have 2 keys that share a pretty long prefix. And if we actually filled out the entire data structure like this, we'd be wasting a whole bunch of extra nodes that don't tell us anything new. So the first kind of path compression we do is if there is a path above a node that just has a whole bunch of steps with no branches, we just fold that path into the node, right? And so by doing this, we can immediately avoid a whole bunch of waste when we have long shared sequences of bits in the key before we get to an interesting decision point. Now, the other example of compression that happens is exactly the same idea, except the long prefix just goes to a single key instead of an internal node. And when this happens, we do the same kind of compression, except at the leaf nodes. And so this is what the fully compressed, a fully compressed tree looks like once we've grabbed all of the shared prefixes and actually saved them at both the key value pairs in the leaves and also in the nodes. And now what this means is that the data structure actually gives us operations that are the minimum of either the size of the data structure, the number of elements, or the length of the key. Because if you have long keys but very few elements, then we'll only have a handful of nodes. And then on the other hand, when we have a lot of elements, no matter what, we will always have operations that are proportional to the length of the key. Now, we'll see in the actual implementation, one simplification here is that we do need to care about the fact that this thing at the node is a prefix, but to both simplify the representation and make some of the algorithms a little bit more efficient, we can just store the key at every single leaf. And this just makes some of the code a little bit more straightforward and makes it very easy to figure out if a key value pair is the one we're looking for. We just compare the key. Okay, so let's look at what this becomes when we turn it into some actual Haskell code, right? So the idea is that we want to look at the implementation of data.intMap, which is a binary tree, binary trie with path compression. Right? So I won't get into all of the code, but we'll look at the type, and we'll kind of sketch out what the implementation of some of the operations looks like. So in data.intMap, we have 3 possible constructors. Either we have a leaf, which contains the key and the value, or we have a branching node, which is one of these intermediate nodes. And the branching node needs to tell us a few things. It needs to tell us what the prefix before the branch was. It needs to tell us what bit of the key we're branching on. And then it has to have the 2 children trees for us to recurse over. And then finally, the tree also has an empty constructor to represent empty trees. And the funny thing is that none of the algorithms really need the empty constructor. So we could just have a kind of non-empty IntMap and then define IntMap as a maybe of that. But on the flip side, the downside is that this non-empty IntMap doesn't have a lot of the nice properties and instances we want. And it's really common to want an empty IntMap. So in the Haskell library, empty is just baked in to the IntMap type. So here is a slightly simplified version of the code that actually implements IntMap. And what we see here is, at first, the three options I talked about. So empty is pretty straightforward. The leaf has a prefix, but really it has the entire key. And it also has the value. And then finally, the branch has to have two integers worth of metadata. It has the compressed prefix on top of the branch. This is what we saw in the diagrams. And then it also has a mask. And what this is it's an int with all zeros, except with a 1 at the bit for which we're branching on. And this mask, combined with the prefix, lets us do a few bitwise operations to figure out where in the prefix to actually compare against our key, and also to do other operations like create new branches or make changes. Now, I should also note that this isn't the only possible representation. We can build a data structure that, instead of storing prefix and mask, stores, for example, the smallest and the largest key in that subtree. And there's a cool blog post by Edward Kmet, if you want to read about that. And the interesting thing is that that does change some of the algorithms and some of the constant factors, but it doesn't change the overall shape of the data structure, and it doesn't really change the asymptotic performance that we expect from the data structure. Okay, so I won't be going into the more complicated algorithms, but I thought that the lookup function was a very good option to just show off what these binary trie operations look like in Haskell. So the first two cases are actually pretty simple. So if we're trying to look something up in an empty tree, we don't care what the key is. We always return nothing. If we're trying to look up a key in a leaf node, we need to check if that leaf node has the matching key. If it does, we return the final value. If it doesn't, we return nothing. So these two cases are all very straightforward. But the real trick comes up when we figure out what we need to do when we encounter an internal branching node. So here is, again, a slightly simplified version of the code. So the idea is that we have a branch. The branch has the prefix. It has the control bit, which tells us where in the prefix or where in the key we need to look. And then it has a left and a right branch for the tree. So we have to do three different things. First, we have to make sure that the key we're trying to look up has a prefix which matches the branch. Because after all, it's possible that we compressed away some other branching node that would have stored the key we're looking up. And so if that happens, we have to double check before we recurse that the key is still part of the subtree defined by the branch. So the first line here just says, if the prefix of the k at the control bit is not equal to the prefix that the branch node expects, we return nothing. So assuming that the key we're looking up is actually in the subtree with the branching node on top, we have two possibilities. Either the bit that we are currently branching on is a 0, in which case we go left, or the bit is a 1, in which case we go right. Now, the nice thing here is that given this representation, where the control mask is a bunch of zeros with a single 1 bit at the bit that we're checking, this particular bitwise check actually becomes very short and fast. We just take the key, we combine it, we AND it with the control mask. If it's a 0, it means that the 0, the bit of the key that we're looking at is a 0. And the reason this happens is because at every other location, control has a 0 bit. And whenever we do a bitwise AND against a 0 bit, the result at that location is 0. So the only way for them to all be 0 is if the 1 bit at the key that we are branching on is also 0. Right? So we have that. And then if that's not the case, we don't actually easily know what number it would be otherwise. It's going to be some part of 2. But that's not relevant. As long as we know that the bit we're looking at is not 0, then we can always just go to the other branch, and we can take the right branch. And then also, I mean, here is kind of, as an example, the actual bitwise logic needed to figure out the prefix of a key. And there's actually, I think, maybe a few different ways to do it. And the details aren't the most important. But the point is that in the real world, one of the things that does determine the performance of an implementation of this data structure is that you have to be relatively efficient in a few different areas when you're writing bitwise computations. And in fact, this is the one place where lookup isn't the best example, because the slightly trickier bitwise logic that actually has an effect on performance happens in some of the other operations. So this is just something to keep in mind if you do want to go out and implement one of these data structures yourself. Okay, so what can we do to go beyond the structure that we get with IntMap? Are there any improvements that could be had by designing a new kind of Radix tree data structure? And so remember when I started, I said we had a binary trie. And in one sense of the word binary, it was a data structure that looks at the key bit by bit. But in another sense of binary, it's also a tree which has two branches at each node. So it is, in a very real sense, a binary tree. So the first thing that we can do is design a version of this Radix tree that branches on more bits at a time. So, for example, if we looked at 2 bits of the key, then each internal node would have up to 4 children. And if we looked at 8 bits of the key, if you looked at a byte at a time, then each branch would have 256 children. So the number of children goes up exponentially with the span. But this is probably one of the more important parameters we would want to tune if we were trying out different kinds of prefix trees for our application. Now, and I grabbed this very handy empirical result from a paper I'm going to talk about a little bit later. But what it shows is that there is this very clean trade-off between the amount of space that your data structure consumes and how tall it is. And the reason this trade-off happens is that in the simplest case, if we have a binary trie, we're always branching on a single bit, then each node only needs to have enough room for 2 children. So the downside is that the tree might get really tall, because if you have a bunch of keys, we need a whole bunch of these small nodes. But the upside is that each node is relatively small. It only needs room for 2 children. Now, on the kind of extreme opposite example, if we were reading in a byte at a time or 2 bytes at a time, each time we had a node, we would allocate a gigantic array for all the children. And so if we were allocating an array of 256 elements for each branching node, and we have a relatively sparse tree, we're actually wasting a lot of space, because each node might only have a handful of children, but it allocates a full 256 element array. And so that is where this relatively clean trade-off between the span and the tree height and the memory consumption actually comes up. And it's always satisfying to see that, when somebody does the benchmark, that the theoretical results correspond pretty well to what happens in the real world, at least until you get to these really extreme, 16 or 32-bit at a time trees. Okay. So, and now I'm actually going to talk about the paper where this, sure.
Isn't there also some overhead when you have the very tall trees that are perfectly binary? Then,
well, there is. It takes longer to traverse the tree, so you basically have to hit more pointers and then take more calls.
Yeah.
So basically, going back here for a second, the trade-off is that the higher the tree, the slower it is to do lookups and modifications. And in a mutable case, at least, the shorter the tree, the faster it is to do updates and to do lookups. I think, unfortunately, this is one of the things where the trade-off gets a bit more muddy in a persistent setting. Because in a persistent setting, if we have a big array and we want to change the value at a single node, we end up needing to reallocate the whole array. So it becomes a little bit less nice. But certainly in a mutable setting, there is a very clear trade-off here between performance and space usage. So actually, this is an example, and I think a pretty elegant example of one of these fundamental time-space dichotomies in making data structures. And these kind of dichotomies, these kind of trade-offs, seem to come up really often in computer science. Okay, I'm going to talk about the adaptive radix tree. And so what these researchers did is they took a look at this inverse relationship. And they said, okay, we have this trade-off. Is there something we can do to get the best of both worlds? Is there some way in which we can have a tree that tends to be as short as a tree with a big span, but doesn't waste extra space for nodes that are relatively sparse? And so their solution, which is, I think, very elegant, is that the intermediate nodes aren't always a single array. So on the one hand, this does make the algorithms, the implementation, a little bit more complicated. But the upside is that if you have a node with only 2 children, you don't have to allocate a gigantic 256 element array to store it. You can allocate something a lot shorter. And so given this idea, and also like in the paper, they actually go through what the kinds of nodes are. And I'm not sure how important the details are, especially if you want to translate this into a persistent setting, into Haskell, for example. You might want to tweak what the internal nodes are. But the basic idea of having different kinds of nodes, depending on how full or like how many children that node has, is a really powerful way to take the general structure of a radix tree and optimize it to actually get away from this time-space trade-off. And in fact, if you look back at the chart from their paper, we see that we have this elegant 1 over x curve here, and their paper sits well underneath it. So it really does, at least according to their benchmarks, give you the best of both worlds. So we can have, do you have a question?
The nice thing that they did with the adaptive radix trees was they're always using byte in the array, so you're never doing you don't necessarily always have to do the prefix or contraction like you do in the radix trees. So you're doing far less bit operations.
Right. So that's another thing where, because modern architectures really prefer to work at a byte by byte level, a lot of the operations get a lot more efficient if you look at 8 bits at a time over here. And so what this tree does is it lets us look 8 bits at a time, get a lot of the associated benefits with working a byte at a time without paying the cost in terms of memory consumption. Okay, and then one nice thing is, if you weren't too worried about performance, and unfortunately performance is the whole point of the exercise, but ignoring that, if you just wanted a correct implementation of the algorithms for an adaptive radix tree in Haskell, algebraic data types are actually a really good fit for expressing these. And the core of the data structure looks almost identical to what we saw with normal data.intmap. In fact, the difference might be that these, the metadata you store can be a little bit different. And then, of course, the children pointers, instead of being 2 branches left and right, are a more complicated data structure. And here's an example of what, in Haskell, the actual intermediate node types from the paper might look like. And the trick is, we have these 3 cases which store the same types of fields, but have different algorithms and different expectations that just don't show up in the Haskell types that we would use to implement this. Now, one downside with this number of nodes is that instead of having a single case when you do a branching operation, you now have 4 cases. Or in fact, you really have 8 cases, because each time you do a modification of a branch, you have to check which of the 4 branches it is, and then you have to check whether you need to allocate a bigger branch, right? And so with 8 cases, it's a lot easier to write a correct specification for this algorithm, given pattern matching and an algebraic data type that will help you make sure you cover all the cases. And then life gets even more exciting if you try to write a merge algorithm, because you end up with 16 cases just to deal with different sizes of branches being combined. So I actually think that if it wasn't for the awkward performance, Haskell would be a great language for working with data structures like this, because at least getting the correctness and getting the original implementation is really easy. Unfortunately, Haskell also ends up with a whole bunch of extra pointer traversals and extra boxing around, especially arrays, and that makes getting the performance you need a lot more difficult. And I'm hoping that in the near future there will be some GHC work that actually makes this more viable. Okay, and also as I mentioned, like nothing about the algorithms for either normal radix trees or these adaptive radix trees relies on mutation. So we can just take the ideas outlined in the paper and turn them into a persistent data structure. And in fact, one of my friends did exactly this in Java. And again, at least according to his benchmarks, the Java implementation of these persistent adaptive radix trees seems to perform pretty well. Unfortunately, good benchmarking is hard, and it's really hard to judge how this would play out in a different setting. But I actually do think that some variation on the adaptive radix tree might be a very good fit for Haskell. And I also know, in Haskell at least, that an efficient, persistent key value map would be incredibly valuable to people who are just doing normal day-to-day functional programming. Okay, so let's just quickly review what we talked about. So we have tries. They're a general kind of data structure that works on the components of a key. This lets us always keep the keys in sorted order, retrieve the keys in sorted order, and also do efficient prefix operations and efficient merging. And now tries, there's actually a lot of different variations on tries. The basic idea comes up in a lot of different contexts. But for us specifically, I talked about a binary try with path compression. And that is the data structure that powers IntMap, which is one of the most commonly used containers in the Haskell world, and probably one of the better performing key value maps that we have access to in Haskell. And then if you want to go beyond IntMap, if you want to design a data structure with a better set of trade-offs than we have with IntMap, we can first just take a look at writing radix trees with different spans. And then, on top of that, we can look at slightly more complicated variations, like the adaptive radix tree, where the intermediate nodes actually have different data structures. And there's a lot of room for exploration and tuning, where if we were designing a data structure from the ground up to be a persistent key value map, there is a very good chance that we would come up with a different set of data structures for the nodes than the authors of the adaptive radix tree paper used, because we would have a very different set of constraints and a different set of trade-offs we're looking at. So I think there's actually a lot of fertile ground here for somebody to come in and write a novel, efficient, persistent data structure. Okay, so are there any questions?
Did you actually do the full implementation of the adaptive radix tree?
So, yeah, I implemented one relatively naively, including I didn't do merging, but I did like lookups and modifications. But then like on my actual benchmarks, it performed really poorly. And I'm pretty sure like part of it is just because I'm not really a Haskell performance expert. But another part is that in the current state of Haskell, there's no way to declare an array that is both boxed and strict. So there's a bunch of overhead in dealing with thunks in the middle of your data structure.
You can't use an unboxed vector?
Well, so the problem is the vector needs to have like a recursive tree type inside it. And you can't make the tree type itself unboxed.
Oh, because it has a pointer.
It has a pointer, exactly.
Yeah.
So we really want an array with kind of two properties. Like my ideal would be an array which has a fixed statically known size, so it can be very easily inlined into other Haskell data structures. And then also it's strict, so that we don't have to pay for a branch each time we look at one of the intermediate nodes. And so right now, I think if Haskell had something like that, then this data structure would perform a lot better. And it would also open up the floor to a lot of efficient tree-based data structures that use arrays in the middle of the tree.
I was curious, so I saw the M256.
Yeah.
Why did you have a maybe A on the array?
Sorry, where was this? Let's go back.
I gave you there, that one. Why do you need the maybe A there? That should
Right.
The 256, N256 should just be an array of...
So N256,
Should be just bytes pointing to the new node.
no, sorry, N48 is the one that has an array of bytes that then indexes into an array of children pointers. The 256 case is for a branch which has a number of children between 49 and 256.
No, it should be 0 and 256, right? Because at least in the C version, you could then take the exact byte and it was the exact index in the array.
Sure, you can. You can do that. So this array has 256 elements, right? But some of those elements might not be present in the map. So in C, you do this with a null pointer. Like in the array is full of nulls. In our case, we need to have the null pointer in some other way. So we use maybe to say that we don't always have exactly 256 children. So look, sorry, so just to be clear, the maybe here is just saying that A is nullable. And A, in this case, would be another, a children,
But I think I would
tree.
have just had a children that is a null.
I mean, that I think is also a totally valid way to do it. Although, again, slightly, like, at least the way I organized it here, right, is that the children is a data structure that doesn't really know it's inside the tree. And so there's kind of like two levels here. There's the tree contains children, and then the children contains a tree, right? Because in fact, this children here, this maybe A, could be a leaf node as well. Or I guess the other thing I could have done is actually, instead of using maybe, just relied on the empty constructor.
I think I would have added another thing. I'd have to think about it, but
So-
maybe.
And also in this case, I'm just trusting GHC to properly optimize maybe. And I think this is one of the times when it actually does a good job. Right? You end up not paying the cost for the extra constructor. Although really maybe it should be like a strict maybe. But the thing is, like, even in the C code, right, you do have to check whether, after you index with a byte, whether it's a pointer or a null pointer. Like, you can't get away from that by the structure of the data.
I'd have to think about it,
Yeah. Okay, any other questions? Okay, cool.